Sections 4.1 through 4.3 lay out the linear regression model and the least squares estimators of its slope and intercept. In section 4.4, we turn to requirements on the data for estimation of a causal effect. In essence, the key requirement is that either big X is set at random in an experiment, or big X is as if randomly set. Our focus on causal inference continues through chapter 13. We return to the prediction problem on chapter 14. 4.1, the linear regression model. Return to the father's question. If he tells you the district class size, could you predict that district's standardized test scores? In chapter 2, we use the notation big E of big Y given big X equals X to denote the mean of big Y given that big X takes on the value X that is the conditional expectation of big Y given big X equals X. The easiest starting point for modeling a function of big X when big X can take on multiple values is to suppose that it is linear. In the case of test scores and class size, this linear function can be written big E of test score given class size equals beta sub naught plus beta sub class size multiplied by class size, equation 4.1, where beta is the Greek letter beta, beta sub naught is the intercept, and beta sub class size is the slope. If you were lucky enough to know beta sub naught and beta sub class size, you could use equation 4.1 to answer the father's question. For example, suppose he was looking at a district with a class size of 20 and that beta sub naught equals 720 and beta sub class size equals negative 0.6. Then you could answer his question. Given that the class size is 20, you would predict the test scores to be 720 minus 0.6 times 20 equals 708. Equation 4.1 tells you what the test score will be on average for districts with class sizes of that value. It does not tell you what specifically the test score will be in any one district. Districts with the same class sizes can nevertheless differ in many ways, and in general will have different values of test scores. As a result, if we use equation 4.1 to make a prediction for a given district, we know that prediction will not be exactly right. The prediction will have an error. Stated mathematically, for any given district, the imperfect relationship between class size and test score can be written. Test score equals beta sub naught plus beta sub class size times class size plus error. Equation 4.2. Equation 4.2 expresses the test score for the district in terms of one component, beta sub naught plus beta sub class size times class size that represents the average relationship between class size and scores in the population of school districts, and a second component that represents the error made using the prediction in equation 4.1.